Thank you. The task for today is to find particular solutions. So let me remind you of where we've gotten to. We're talking about the second order equation with constant coefficients, which you can think of as modeling springs or simple electrical circuits. But what's different now is that the right-hand side is an input which is not zero. So we're considering the I'm going to use X as your book does, keeping to a neutral letter. But again, in the applications and in many of the applications at any rate, it wants to be T, but I make it X. So the independent variable is X, and the problem is remember that to find a particular solution, and the reason why we want to do that is then the general solution will be of the form y equals that particular solution plus the complementary solution, the general solution to the reduced equation, which we can write this way. So all the work depends upon finding out what that yp is, and that's what we're going to talk about today. Now, or rather talk about for 2 weeks. But the point is, not all functions that you could write on the right-hand side are equally interesting. There's one kind which is far more interesting or more important in the applications than all the others, and that's the one out of which, in fact, as you'll see later on this week and next week, an arbitrary function can be built out of these simple functions. So the important function is on the right-hand side to be able to solve it when it's a simple exponential. But if you allow me to make it a complex exponential, here are the important right-hand sides we want. We want to be able to do it when it's of the form e to the ax. In general, that will be, in most applications, a is not a growing exponential, but a decaying exponential. So typically a is negative, but it doesn't have to be. I'll put it in parentheses, though, often. That's not any assumption that I'm going to make today. It's just culture. Well, we want to be able to do it for sine omega x and cosine omega x. In other words, when the right-hand side is a pure oscillation. That's another important type of input, both for electrical circuits, think alternating current, or the spring systems, that's a pure vibration you're imposing a pure vibration on the spring mass dashpot system, and you want to see how it responds to that. Or you can put them together and make these decaying oscillations. So we could also have something like e to the ax times sine omega x or times cosine omega x. Now the point is, all of these together are really just special cases of one general thing, exponential, if you allow the exponent not to be a real number, but to be a complex number. So they're all special cases of e to the, I'll write it alpha x, well, why don't we write it of a plus I omega x, right? If omega is 0, then I've got this case. If a is 0, I've got this case, separating into its real and imaginary parts. And if neither is 0, I have this case. But I don't want to keep writing a plus I omega all the time, so I'm going to write that simply as e to the alpha x, and you understand that alpha is a complex number now. Looks different, doesn't look like a real number. Okay, so it's a complex number. So the equation we're solving is, which one? This pretty purple equation. And we're trying to find a particular solution of it. And The special functions we're going to use are these. Well, this one in particular, e to the alpha x. That's going to be our input. Now, it turns out this is amazingly easy to do because it's an exponential, because I write it in exponential form. And the idea is simply to use a rule which, in fact, you know already, the rule of substitution. So I'm going to write the equation in the form. So there it is. It's y double prime plus ay prime plus by equals f of t. But I'm going to f of x. But I'm going to think of the left-hand side as the polynomial operator a, d plus b. A and b are constants applied to y equals f of x. That's the way I write the thing. And this part I'm going to think of in the form, this is p of d. A polynomial in d. In fact, it's a simple quadratic polynomial. But most of what I'm going to say today would apply equally well if it were a higher order polynomial, a polynomial of higher degree. And just to reinforce the idea, I've given you one problem in your problem set where you'll need it when p is a polynomial of higher degree. I should say the notes are written for general polynomials, not just for quadratic ones. I'm simplifying it by leaving, today I'll do what's in the notes, but I'll do it from the quadratic case to save a little time and because that's the one you'll be most concerned with in the problems. All right, so p of dy equals f of x, and now there are just a couple of basic formulas that we're going to use all the time. The first is that if you apply p of d to a complex exponential or a real one, doesn't matter, the answer is you get just what you started with d substituted by alpha. So it's p of alpha. In other words, put an alpha wherever you saw d in the polynomial. And what is this? This is now just an ordinary complex number. And multiply that by what you started with, e to the alpha x. So that's a basic formula. It's called in the notes the substitution rule. Because the heart of it is you substitute for the d, you substitute alpha. Now, this hardly requires proof, but let's prove it just so you see, to reinforce things and make things go a little more slowly to make sure you're on board all the time. How would I prove that? Well, just calculate it out. What, in fact, is d squared plus ad plus b times e to the alpha x? Well, it's d squared e to the alpha x by linearity plus ad times e to the alpha x plus b times e to the alpha x. Well, what are these? What's the derivative of e to the alpha x? It's just alpha times e to the alpha x. What's the second derivative? Well, if you remember from the exam, you can do 10th derivatives now. So the second derivative is easy. It's alpha squared times e to the alpha x. In other words, this law, what I'm saying really is that this law is obviously, quote unquote, true. Okay, I'm not even going to put it in quotes. Yeah. It's obviously true for the operator d and the operator d squared. In other words, d of e to the alpha x equals alpha times e to the alpha x. D squared times e to the alpha x equals alpha squared times e to the alpha x. And therefore, it's true for linear combinations of these as well by linearity. So therefore, also true for p of d. And in fact, if you calculate it out, what is this? This is alpha squared e to the alpha x plus alpha e to the alpha x plus times the coefficient plus b times e to the alpha x, so it's in fact exactly this. It's e to the alpha x times alpha squared plus a alpha plus b. Now, how are we going to use this? Well, the idea is very simple. Remember, we're trying to solve this. I should have some consistent notation for these equations. Purple, I think, will be the right thing. Purple. We're solving purple equations. The formulas which will solve them will be orange formulas, and I don't know, we'll see what we need for as we go along. So I'd like to just formulate it, the solution, the particular solution now. I'm going to call it a theorem. It's really too simple to be a theorem. On the other hand, it's too important not to be a theorem. So let's call it, as I called it in the notes, the exponential input theorem, which says it all. Theorem says it's important. Exponential input means it's taking f of x to be an exponential. It's an exponential input, and the theorem tells you what the response is. So for that equation, I'm not going to recopy the equation. For the purple equation, adequately indicated this way. There, now try to take notes. For the purple equation, a particular solution is e to the alpha x. Somewhere I neglected to say that f of x. All right, so for the purple equals e to the alpha x. How's that? For that equation, y double prime plus ay prime plus by equals e to the alpha x. So here's the exponential input. The solution is e to the alpha x divided by p of alpha. Now, that's a very useful formula. In fact, Haynes Miller, who also teaches this course, in his notes calls it the most important theorem in the course. Well, I don't have to totally agree with him, but it's certainly important. It's probably the most important theorem for these 2 weeks anyway, but you'll have others as well. Okay, so that's a theorem. I don't know, is that a green? Theorem's going green. You can tell what they are by their color code. Well, in other words, what I've done is simply write down the solution for you. Write down the particular solution, but let's verify it in general. So the proof would be what? Well, I have to substitute it into the equation. So the equation is p of d applied to y is equal to alpha x. And I want to know, when I substitute that expression in, is it the case that when I plug it in, that the right-hand side, and calculate it out, apply p of d to it, is it the case that I get e to the alpha x on the right? Well, all you have to do is do it. P of d, what is p of d applied to e to the alpha x divided by p of alpha? Well, p of d applied to e to the alpha x is p of alpha times e to the alpha x. That's the substitution rule. What about this guy? This guy's a constant, so it just gets dragged along because this operator is linear. If this applied to that is this, then if I apply it to 1/2 that, I get 1/2 the answer, and so on. So the p of alpha is a constant and just gets dragged along. And now they cancel each other, and the answer is, indeed, it is e to the alpha x. That's not much of a proof. Now, I hope that to at least half this class, you are wondering, yes, but what if Peter had not caught the wolf? I mean, what if? I'm looking stern. Okay. We'll take care of it in the simplest possible way. We will assume that P of alpha is not 0. The case P of alpha is 0 is, in fact, an extremely important case, one that makes the world go round, one that contributes to all sorts of catastrophes, and they occur first here in the solution of differential equations, and that's what controls all the catastrophes and the good, but there's a good side to it too. It's also what makes a lot of good things happen. So there are no moral judgments in mathematics. For the time being, let's assume P of alpha is not 0, and then that proof is okay, because the P of alpha being in the denominator, it's okay to be in the denominator if you're not 0. Okay, let's work in a simple example. Well, I'm picking the most complicated example I can think of. Simple examples I'll leave for your practice and for the recitations. You can start off with simple examples if you're confused by this. But let's solve an equation. Find a particular solution. 2. Y double prime minus y prime plus 2y is equal to 10 e to the minus x sine x. Gulp. Okay. So the input is this function 10 e to the minus, that's a decaying oscillation. You've seen those already on the computer screen if you've started your homework, if you've done problem 1 on your homework. It's a decaying exponential, and I want to find a particular solution. Well, let's find a particular, and the general solution. Find the general solution. Well, the main part of the work is finding the particular solution, but let's quickly, the general solution, let's find first the complementary part of it. In other words, the solution to the homogeneous equation, that's d squared minus d plus 2. No, let's not. I don't want to solve messy quadratics. Okay, we're going to find a particular solution. I thought it was going to come out easy, and then I realized it wasn't because I picked the wrong signs. Okay. So if you don't like it, just change the problem. I can do that, but you cannot. Don't forget that. So we want a particular solution, and our equation is this equals that. Now, let's complexify it to make this part of a complex exponential. So that the complex exponential that's relevant is 10 times e to the minus 1 plus I. You see that? X. What is this? This is the imaginary part of this complex exponential. So this is imaginary part of that guy. E to the negative x times e to the ix, and the imaginary part of e to the ix is sine x. The 10, of course, is just comes along for the ride. Okay. What's our... Well, now, since this is a complex equation, I shouldn't call this y anymore. By my notation, I like to call it y tilde to indicate that the solution we get to this is not going to be the original solution to the original problem, but you'll have to take the imaginary part of it to get it. So we're looking now for the complex solution to this complexified equation. Okay, what is it? Well, the complex particular solution I can write down immediately. It is 10, that of course just gets dragged along by linearity, times e to the minus 1 plus I times x, and it's over this polynomial evaluated at this alpha. So just write it down with have faith. So what do I get? The alpha is minus 1 plus I. I square that because I'm substituting this alpha into that polynomial. The reason I'm doing that is because the formula tells me to do it. That's going to be the solution. Okay, so it's minus 1 plus I, the quantity squared, minus 1 plus I, plus 2. All I've done is substitute. Minus 1 plus I for d in that polynomial, the quadratic polynomial. And now, all I want is the imaginary part of this. The imaginary part of this will be the solution to the original problem, because this was the right-hand side, was the imaginary part of the complexified right-hand side. Okay, now let's make it look a little better. Yp tilde. Clearly what we have to do is something nice to the denominator. So I'll copy the numerator. That's e to the minus 1 plus I x. And how about the denominator? Well, again, don't expand things out because it's already this long, and what's the point of making it this long? You want to make it this long, right? Okay. Then there's room here for one real number and another real number times I. There's no more room. Okay, what's the real number? Okay, we're looking for the real part of this expression. So just put it in and keep it mentally. So minus 1 squared, that's 1, plus I squared, that's minus 1. 1 minus 1 is 0. I can forget about that term. This term gives me plus 1 for the real part, plus 2. The answer is that the real part is 3. How about the imaginary part? Well, from here, there's negative 2i, from expanding that out by the binomial theorem or whatever you like to call that, minus 2i minus I makes minus 3i. Is that right? Minus 2i minus I minus 3i. So it is 10/3. And now in the denominator I have 1 minus I. I'll put that in the numerator, make it 1 plus I. But I have to divide by the product of 1 minus I and its complex conjugate. In other words, I'm multiplying both top and bottom by 1 plus I. And so that makes here 1 squared plus 1 squared is 2. That takes care, and now what's left is e to the negative x times cosine x plus I sine x. Now, of that, what we want is just the imaginary part. Well, let's see. 2 goes into 10 makes 5, so that's 5/3. So we're practically at our solution. The solution then finally is going to be yp is the imaginary part of yp tilde. And what's that? Well, what's the coefficient out front, first of all? It's 5/3. So let's pull out the 5/3 before we forget it. And we'll pull out the e to the negative x before we forget that. And then the rest is simply a question of seeing what's left. Well, it's 1. I want the imaginary part. So the imaginary part is going to be 1 times cosine x. And then the other imaginary part comes from these two pieces, which is 1 times sine x. That should be the particular solution. Notice that the work, most of the work is not getting this thing, it's turning it into something human that you can take the real and imaginary parts of. If we don't like this form, you can put it in the other form, which many engineers would do almost automatically. Make it 5/3 e to the negative x, and what will that be? Well, you can use the general formula if you want. Remember, cosine, there's the two coefficients are 1 and 1, so it's 1 and 1. So this is the square root of 2, so it is times, this part makes the square root of 2 times cosine of x minus pi over the angle. This is the phi, so that's pi over 4, minus pi over 4. Okay? All right, now let's address the case which is going to occupy a lot of the rest of today and, in a certain sense, all of next time. What happens when P of alpha is 0? Well, in order to be able to handle this decently, it's necessary to have one more formula which is very slightly more complicated than the substitution rule, but it's the same kind of rule. I'm going to call this, or it is called, the exponential. So I'm going to first prove a formula which is the analog of that, and then I'll prove a green formula, which is what to do here if P of alpha turns out to be 0. But in order to be able to prove that, we're going to need the analog of the orange formula. And the analog of the orange formula, that tells you what to do, how to apply P of d to a simple exponential. I need a formula which applies P of d to that simple exponential times another function. Now, I found I got into trouble if I continuing to call that alpha. So I'm now going to change the name of alpha to change alpha's name to A, but it's still complex. I don't mean it's guaranteed to be complex. I mean it's allowed to be complex. So A is now allowed to be a complex number. I'm thinking of it as in general as a complex number. Okay? I hope this doesn't upset you too much, but you know, you change X to T's and Y's to X's. This is no worse. All right, what are we going to do? Well, I'm going to use this exponential shift rule, I'll call it. Exponential shift rule or formula or law. Rule, that's the substitution rule for me, so this is going to be the exponential shift law. And to apply, it tells you how to apply the polynomial to not d, not just the exponential, but the exponential times some function of x. What's that? And now, the rule is very simple. It's, see, if you understand the difficulty. If you try to start differentiating, you're going to have to calculate second derivatives of this stuff. And God forbid, higher order equations, you'd have to calculate fourth derivatives, fifth derivatives, and you barely even want to calculate the first derivative of it. That's okay. But second derivative, do I have to? No. Not if you know the exponential shift rule, which says you can get rid of the e to the ax, make it pass to the left of the operator where it's not in any position to do any harm any longer or upset the differentiation. And all you have to do is, when it passes over that operator, it changes d to d plus a. So the answer is e to the ax, it's there, it's passed over. But when it did so, it changed d to d plus a. And what about the u? Well, the u just stayed there. Nothing happened to it. Okay, there's our orange formula. I guess we better put a thing around the whole business. Should I prove that, or should I? The proof is quite easy, so let's do it just, again, to give you a chance to try to see what it's... Now, if somebody gives you a formula like that, you first stare at it. You might try a couple of special case. Try it on a function and see if it works. But already, you probably don't want to do that. I mean, even if you took a function like x here, you'd have to do a certain amount of differentiation, in some quadratic thing here. You'd calculate and calculate away for a little while. And then if you did it correctly, the two would, in fact, turn out to be equal. But you would not necessarily feel any the wiser. A better procedure in trying to understand something like this is say, well, let's keep the u general. Suppose we make d simple. For example, well, if d is a constant, of course, there's nothing to happen because if this is just a constant, both sides of these are the same. I mean, this doesn't make any sense if p doesn't really have a d in it. Well, what's the simplest polynomial which would have a d in it? Well, d itself. So let's take a special case. P of d equals d. and check the formula in that case, see if it works. So the formula is asking us what is d, that's the p of d, of e to the ax times u. I'm not going to put in the variable here because it's just waste of chalk. Well, what is that? Well, I know how to calculate that. I use the product rule, okay? So it's the derivative. Tell you what, let's do it the other order first. So it's e to the ax times the derivative of u plus the derivative of e to the ax, which is a times e to the ax times u. You follow that? This is the product rule. It's e to the ax times the derivative of u plus the derivative of e to the ax, which is this thing, times u, the other factor. Now, is that right? I want to make it look like that. Well, to make it look like that, I should first factor the e to the ax out. And now what's left? Well, if I factor the e to the ax out, what's left is du plus au, which is exactly d plus a operating on u. Du plus au. Hey, that's just what the formula said it should be. If you make e to the x pass over d, it changes d to d plus a. Okay, now here's the main thing I want to show you. All right, now, well, let's try, if this is true for, also works out for d squared, then the formula is clearly true by linearity, because an arbitrary p of d is just a combination, linear combination with constant coefficients of d, d squared, and that constant thing which we agreed there was nothing to prove about. Now, hack. You're a hack if you take d squared and start calculating the second derivative of this, okay? Of course you're not hacks. I mean, it's just you haven't learned the right thing to do. Okay, that will work, but it's not what you want to do. Instead, you bootstrap your way up. I have already a formula telling me how to handle this, and you can be anything. Therefore, look at this not as d squared all by itself. Calculate instead d squared e to the ax times u. Think of that as d, the derivative of e to the ax u. In other words, we'll do it one step at a time. But you see now immediately the advantage of this. What's d of e to the ax u? Well, I just calculated that. Now, don't go back to the beginning. Don't go back to here. Use the formula. After all, you worked to calculate it, or I did. So it's d of, and what's this inside? It's e to the ax times d plus a times u. Well, that looks like a mess, but it isn't, because I'm taking d of e to the ax times something. And I already know how to take d of e to the ax times something. It doesn't matter what that something is. Here the something was u. Here the something is d plus a times u, operating on u. But the principle is the same, and the answer is what? Well, to take d of e to the ax times something, you pass the e to the ax over the d. That changes d to d plus a. And you apply that to the other guy, which is d plus a applied to u. What's the answer? E to the ax times d plus a squared u. It's just what you would have gotten if you had taken e to the x, pass it over, and then change d to d plus a. Now, another advantage to doing it this way is you can see that this argument is going to generalize to d cubed, d. In other words, you would continue on in the same way by the process of mathematical, one word, mathematical, begins with an I, induction. By induction, you would prove the same formula for the nth derivative. If you don't know what mathematical induction is, shame on you. But it's okay. A lot of you will go through life without ever having to learn what it is, and the rest of you will be computer scientists. Okay, so that's the idea of this rule. Now we can use it to calculate something. Let's see, I'm going to need green for this, I guess, for our better formula. The formula now that tells you what to do if P of alpha is 0. So we're trying to solve the equation d squared plus AD. We're trying to find a particular solution. E to the AX, let's say. Remember, A is complex. A can be complex. Doesn't have to be real. But the problem is that P of alpha is 0. How do I get a particular solution? Well, I'll write it down for you. So this is part of that exponential input theorem. I think that's the way it is in the notes. I gave all the cases together, but I thought pedagogically it's a little better to do the simplest case first and then build up on the complexity. So what's YP? The answer is YP is e to the AX, except now you have to multiply it by x out front. Where have you done something like that before? Yes, don't tell me. I know you know. But what should go in the denominator? Clearly not P of alpha. What goes in the denominator is the derivative. Okay, but what if P prime of alpha is 0? Couldn't that happen? Yes, it can happen. So we better make cases. This case is the case where this is okay, corresponds to the case where we're going to assume that alpha is a simple root. Is a simple root of P of the polynomial P. I don't know what to call the variable. P of D is okay. A simple 0. In other words, it's not double. Well, suppose it is double. And one of the consequences, as you'll see just in a second, if it's a simple 0, that means this derivative is not going to be 0. That's automatic. Yeah, well, suppose it's not as simple. Well, suppose it's a double root. How did that get changed to? That's not an alpha. That's, oh, well. Yes, it is, obviously. Change. You know, I should. All of you, I want you to change to alpha. They should have something, you know, like a search key where 147 occurrences of alpha have been changed to A with a stroke of with just your thumb. They don't have that for the blackboard, unfortunately. Well, too bad. For the future. Correctable blackboards. Okay, what if A is a double root? It can't be more than a double root because we've only got a quadratic polynomial. Quadratic polynomials only got 2 roots. And so the worst that could happen is that both of them are A. All right. In that case, the formula should be YP is equal to, you're now going to need x squared up there times e to the ax, and in the denominator, what you're going to need is the second derivative of evaluated at a. Now you can guess the way this is going to go on. For higher degree things, if you got a triple root, you'll need here x cubed and here p triple prime, except you're going to need a factorial there too, so don't worry about it. It's in the notes, but I'm not going to give you that for higher roots. I don't even know if I'll give it to you for double root. Yes, I already did, so it's too late. It's too late. Okay, so we'll make this two formulas according to whether A is a single or a double root. Okay, let's prove one of these, and that will be good enough for my conscience. Let's prove the first one. Mostly as an exercise in using the exponential shift rule. This will be a first example of actually seeing it work in practice as opposed to proving it. Okay, so what does that thing look like? So what does a polynomial look like which has A as a simple root? So we're going to try to prove the simple root case. So I'm just going to calculate what those guys actually look like. What does P of D look like if A is a simple root? Well, if it's a simple root, that means it has a factor. When it factors into the product of D minus A times something which isn't D minus some other root, and the point is that B is not equal to A. The roots are really distinct. Okay. Suppose P, what's then P prime? I'm going to have to calculate P prime of A. What is that? Well, let's calculate P prime of D first. It is, well, by the ordinary product rule, it's the derivative of this times, which is 1 times D minus A, plus, that's one thing, plus the same thing on the other side, the derivative of this, which is 1 times D plus B, D minus B. So that's P prime, and therefore what's P prime of A? It's nothing but this part is 0, and that's A minus B. Of course, this is not 0 because it's a simple root, and that's the proof for you, if you want, that if the root is simple, that P prime of A is guaranteed not to be 0. And you can see it's going to be 0 exactly when B equals A, and that root occurs twice. But I'm assuming that didn't happen. Okay, then all the rest we have to do is calculate, do the calculation. So what I want to prove now is that with this P of D, what I'm trying to calculate that P of D times that guy, x e to the ax, except I'm going to write it as e to the ax times x, guess why, divided by P prime of A. This is my proposed particular solution. So what I have to do is calculate it and see that it turns out to be, what do I hope it turns out to be? What's the right-hand side of the equation? The input. The input is e to the ax. If this is true, then yp, the particular solution, indeed, that thing will indeed be a particular solution. Of course, there can be others, but I only remember, in this game, I only have to find one particular solution, and that certainly by far is the simplest one you could possibly find. So I have to calculate this, and now you see why I did the exponential shift rule, because this is begging to be differentiated by something simpler than hack. Okay, and you also see why I violated the natural order of things and put the e to the ax on the left, in order that it pass over more easily. So the answer on the left-hand side is e to the ax times P of D plus A. Now, what is P of D plus A? Write it in this form. It's going to be A minus B. So P of D plus A is, change D to D plus A. So the first factor is going to be D plus A minus B. And what's the second factor? Change D to D plus A, it turns into D. All this is the result of taking that P of D and changing D to T plus A. And now this is to be applied to what? Well, the e to the ax has already passed over, so what's left is x, and that's to be divided by this constant, P prime of A. Now, what does this all come out to be? E to the ax. What's D applied to x? 1. Right? And now what's this thing applied to the constant 1? Well, the D kills it, so it has no effect. It makes it 0. The rest just multiplies it by a minus b. So the answer to the top is a minus b times 1. And the answer to the bottom is p prime of a, which I showed you by just explicit calculation, is a minus b. And so the answer is e to the ax. Comes out right. Now the other one, the other formula comes out the same way. I'll leave that as an exercise. Also, I don't dare do it because it's much too close to the problem I asked you to do for homework. So let's, by way of conclusion, I'll do one more simple example, okay? And then you can feel you understand something. I'm sort of bothered by having done any examples of this more complicated case. So I'll pick an easy version instead of the one that you have in your notes, which is the one you have for homework, which is even easier. So this one's just epsilon less easy. Y double prime minus 3y prime plus 2y equals e to the x. Okay. Notice that 1 is a simple root. The one I'm talking about is the a here, which is 1. 1 is a simple root of the polynomial d squared minus 3d plus 2, isn't it? It's a 0. Put d equal 1, and you get 1 minus 3 plus 2 equals 0. It's a simple root because anybody can see that 1 is not a double root. Because you know from critical damping, if 1 were a double root, you know just what the polynomial would look like, and it wouldn't look like that at all. It would not look like d squared minus 3d plus 2. It would look differently. Therefore, that proves 1 is a simple root. Okay, what's the particular solution, therefore? The particular solution is x times e to the x divided by the derivative evaluated at the point. So what's p prime of d? It is 2d minus 3. If I evaluate it at the point 1, it is negative 1. So if this is to be divided by negative 1, in other words, it's minus x e to the x. And if you don't believe it, you could plug it in and check it out. Okay. Okay, I'm letting you out 1 minute early. Remember that. I'm trying to pay off the accumulated debt